Welcome to this small webinar. Thank you very much for joining, all of you. We're going to spend a while together, try to understand the fine art of specifications and certificates. Welcome once again. Today's presenter is me. I'm Paul Madsen. I'm Area Sales Manager and Global Product Manager for Amatec Calibration Instruments. I have a background in electronic engineering. I worked with test, measurement, and calibration for almost 40 years. The latest 25 years, I have been working with Amatec out of my home office in the central part of Denmark. 25 years ago, it was a bit uphill to home offices, and today it's more or less standard procedure. Let's just take it from here. The webinar will be recorded, so Sean who is assisting, will be putting it on our web as a YouTube video. You are all muted because if you have this pretty large number of attenders and everybody is talking, it makes an awful lot of noise. You can ask questions via the chat function, and again, Sean will be looking after the chats or the questions. We will have a small question and answer session at the end of the webinar, and we will share the presentation slides with you with an email after the presentation is over. And the recordings, as I said, will be available on our web as a YouTube video. The agenda looks like this. Well, why does specifications matters? Yeah. Introduction for some accuracy statements, components of accuracy statements, and a definition of terms, a bit of stability over time, pressure, temperature ranges, and that kind of stuff, comparing accuracy statements, a bit about factory calibration and certificates, and a bit of sum up, making a conclusion at the end of the webinar. Why does specifications matters? Well, if you're involved in tests and calibration, the product specifications are, well, sometimes they're a bit strange and a mysterious world. A lot of technical information, references to words that are perhaps not understood or strange. So that I'm trying to make it a bit clearer. At the end of the day, the specifications and the related calibration will be the tool for you to select and prove the right tool for your test and calibration job, because that's a bit what it's all about. Without understanding the specifications, it's not possible to pick the proper tool. The job might be jeopardized. The quality systems, verification of the systems, and so on will put in danger. So it's quite essential that we understand the specifications. Going forward on the slides, I will explain and visualize some of these strange and mysterious words. We start in the very beginning with accuracy versus precision. Accuracy is, in other words, it's the closeness of the agreement between the result of a measurement and the true value of what's measured. So that is a bit what it's all about. That's what's very much all about, and the closeness, the precision is the closeness of the measurement between repeated measurements of the same quantity under the same conditions, and that's often called repeatability. And obviously, they're both needed, but accuracy and precision together makes the whole story. If you have a look on the drawings, well, the first one, it's accurate, but it's not precise. Well, okay, it actually hits very well within the center, but it's not very precise, but because the measurements are spread all over. Number two is both precise and accurate, and that's basically what we want. Number three is not accurate and not precise, and nobody wants that one. Precise but not accurate. Well, okay. In the normal world, it's not something you like, but it could be some times you would actually say, well, okay, it's gonna be a relative measurement, and we just need to do a number of measurements, and for that a precise instrument could be okay. And now we'll walk a bit through some of the wordings of the specifications. Hysteresis is the difference when your measurement are taken at the same pressure, but one going upwards and the other is going downwards, increasing and decreasing pressure. In the analog time, this effect might be significant, and it was a very nice way to figure out if the system was actually getting worn out or had mechanical wear, because then you would see a larger hysteresis. In the digital world, our digital world of today, the effect is not that big anymore. It's still there because the diaphragm and the fillings and so on still have a slight hysteresis. And it's essential also to measure hysteresis when the reference gauge is calibrated, because it actually nicely indicates if there's have been some mechanical damage or overpressure of the pressure sensor. Linearity. The linearity, well, yeah, error is the deviation of the output curve from a specified straight line over the range. It's also someone calls it non-linearity. If you look on the graph over there, well, it's supposed to be the green dotted line, but in the real world, it would have some kind of behavior that is not a straight line. And have a look at the picture. You see that's this actually nicely illustrates that you need to calibrate more than 0 and full scale. Otherwise, you will not detect linearity errors. You could have if you actually adjusted 0 and 100%, well, you would not see anything in between. Repeatability. Well, that's the degree of agreement between the measured value of the same pressure under the same conditions again and again and again. Digital reference gauges and calibrators, for those are the repeatability is essential for those as well. And if the repeatability becomes notable, the pressure sensor shall be examined or changed, because that's not a normal behavior for a electronic device. If you look on the graph or on the picture over there, you see, well, okay, what we want is the green spot again and again in the center. But in the real world, you will have a certain spread around the green dot. And then we have some drift, long-term drift. Well, that's a slow change in the response of measured values over time. It's a slow variation of the performance characteristics, and it might be gain or an offset. You never know. That's up to us as manufacturers to figure that out and actually define it. Drift is stated for a period, typically 1 year, but any specified time will do. You can do, well, shorter time if you want to have a better accuracy, or longer time if you want to save some calibrations runs. And obviously it will affect on the overall specification. And the drift specification is the base of the calibration interval, on which we recommend for our equipment, or all manufacturers would recommend. Temperature drift. It refers to, well, it's certainly underside temperature influence. Silicon pressure sensors, they are highly sensitive. A uncompensated silicon sensor will change approximately 0.2% per degree, which actually makes it a very fine thermometer. So temperature calibration is a must. If you don't have any temperature compensation, you really can't use it for pressure measurement. Temperature and compensation is worth spending a bit of attention on, so we'll do that. On the graph over there, see that in the ideal world, it should be the green dotted line once again, and in the real world, it will be something like a mountain, like the red one. It's really massive. But additionally, the temperature drift was corrected by some simple analog circuitries on, well, resistance and so on. And the temperature range where he actually was working was pretty narrow. And you had to apply correction factors outside the specified temperature range, whatever that might be. It might look like something, we had a temperature coefficient of outside the temperature range, and you added on 0.05% of range per degree, and that was a bit complicated, but that we worked with that for many years. So if you took the about line, you could see that it would actually call out for an additional 1.14% added for the understated accuracy for well, it's not that cold, but it would be significant compared to what we normally specify modern reference gauges and pressure calibrators for. Temperature compensation. We and everybody else do that to correct the indicated pressure influenced by the operating temperature and the temperature characteristics of the sensor and the electronics. It becomes a complete package of temperature drift, and that's not desirable. Preferably, it will be done over a complete operation temperature range, because then we would avoid these time-consuming and error-making unwanted temperature correction calculations. It's done in a temperature chamber, applying sets of temperature and pressures, and outside we actually pick up thousands of data pairs to go into the calculation system. And when we have done the run, pressure versus temperature, and we don't just do it at one pressure, we do it on many pressures, on all different temperatures. The coefficients are stored in each product, and then they would be validated during the final calibration. The picture over here is it's a temperature chamber with, I think it's probably 48 XP2s eyes in there. Okay, that was a bit drastic, wasn't it? Sorry about that. The active temperature compensation starts with a lot of well-behaved mathematics. At Amaset Crystal, we map the sensor output, and together with the electronics, obviously the analog to digital converters and all kind of the amplifiers and so on would be a part of the system and be a part of the equation as well. And we map them in multiple temperatures, and we map them in multiple pressure points. So that's what it's all about. So we get a kind of a three-dimensional correction curve out of these results, and they are made into a equation that is then uploaded to each gauge. And that's the reason why you just can't apply another sensor for an already existing gauge or calibrator, because you need to go back to the factory to have this done. It's a bit of note here about the specification on the electrical inputs, because on modern pressure calibrators you will have the electrical in and outputs as well. And these specifications are as important as the pressure specification. If you use a pressure calibrator to test pressure transmitters or transducers, with your built-in electrical inputs, you will combine the pressure and the electrical specifications. So if you have a poor electrical specification, even you combine that with the best pressure specification, you will still have a poor calibration result. You need to think that about that. So look for the electrical in and output specifications like you do for pressure. I think often it's a bit forgotten. And also think about the temperature compensation of the electrical inputs. They should be the same, or you have to apply temperature compensation for the electrical part. Even you might have a pressure calibrated that is nicely temperature calibrated over the temperature range, and that seems to be annoying, and that's a point that will add on possibilities for errors and faults. I think we've covered the most significant specification components for the data sheets, and there are plenty other. There might be supply volts and all that kind of stuff. That's normally, I think today it's normally taken care of by the manufacturer. At Crystal, if you're outside your voltage range, we just shut the instrument off, so you can't get hurt, and that kind of stuff. The data sheets are written in many ways, so what I'm trying to do here is actually to show you what you should know and what you should look for when you select the equipment for the pressure test and calibration. The specification sheets include these an accuracy statement for the device, and look for a complete set of specifications like we walked through here in your data sheet. And obviously I know Crystal best, so I took a clip from a Crystal XP2i datasheet, and it states includes all effects on linearity, hysteresis, repeatability, temperature, and stability for 1 year. Well, that's basically what we have been talking about up to now. So what you should be sure about is that all the potential effects are the is in the statement on the accuracy statement. If you have a specification where some of these effects are missing, they must be found somewhere in the data sheet or in the manual and so on, and they must be included for an overall device assessment. And it's also necessary, obviously, to compare the various equipment, but it's also necessary to be sure that that's the right tool for the job. A couple of examples here. The product A here includes stability, but only for 6 months. Yeah, well, okay, that's how it's done, and but if you needed a 1 year specification, you actually it specifies an adder. So one thing, you can use the adder, or you can do without the adder and then calibrate your device for every 6 months, whatever is most handy. So think about that. Product B, let's say up to specification, but well, really no conditions. I think it was a bit It was more common in the past, but we still see them. Accuracy is 0.025%. Well, yeah, including calibration certificate, yes, but it really does not specify the conditions. Product C, it has a small, limited temperature compensated range and a relative large adder outside that range. So, it's an entry-level product here. So say, well, okay, the positive pressure here is 0.1% of full scale, but it's if you move it outside the comfort area, outside 15 to 35 degrees, it actually might end up, it easily ends up with a double accuracy. So that's notable. That needs to be noticed. Okay, I think I'm a bit. Yeah. I'm back to the drift over time here. All pressure devices drift over time. So the key is actually to state the period. The specifications include a stability period, like we had the 1 year or whatever it might be on the data sheet. It's the easy way to affect the product's performance if the manufacturer shorten this interval. But beware that the shorter intervals require more frequent calibrations. So after a while, after some years, the cost there would actually be large, because if you think that you're going to have this instrument for 12, 15 years, and you say, well, okay, if you had a 1 year calibration interval, you would calibrate it 11, 12 times, and if you had a half a year of calibration interval, you'll double that number of calibrations. So if we're talking a standard reference gauge, the cost of the cost of ownership for this gauge would actually be much higher, even that it started up being a less expensive gauge in the front. So that's worth notice as well. Pressure ranges. Obviously, you need to. We all specify a pressure range, higher or lower. Readings have and outside these ranges, we have an unknown error, or go further, it would damage the gates, or it might blow up. Some devices, I think most electronic devices today, would warn the user against taking readings outside the range. Flashing display, frozen display, line of dots, or whatever it is. And then there's the question also, if you bring it outside there and the device is actually overpressed, does it actually give a warning, or does it not? It is possible to do electronic pressure devices where you can actually measure on the chip actually of the pressure sensors. It's not bulletproof, but I'd say that we come a long way actually to come up with an error code, present an error code for the user, and we just indicate the error code, and we don't indicate any pressure. So the user will not use a bad gates. And overpressure, obviously you should pay attention to the populist overpressure in the specifications because, well, they don't work outside that. It might damage the instrument, and at the end, it actually might even be dangerous. Back again on the compensating temperature range. Define the range where the device corrects for the temperature effects. And in this range, we would say there will be no additional error added to the specification, as long as you keep it inside the temperature range. At Crystal Amatec Crystal, we come to the point that we actually compensate the temperature range. So it's the compensated range is the same as the range we specified the gates or the calibrator to be operated. So there will be no additional calculations. That's what we believe in, and I think many errors over time have been done by calculating these kinds and so on, perhaps faulty calculations or missing calculations. And some devices will have compensated range that's smaller than the operation range, and that means that the user or somebody should actually know what the temperature is and calculate the additional errors, and this might end up as a significant contribution, like we saw before in the former slide. We take one again here. Well, an old-fashioned one, Crystal 30. That is yeah, what it is. It's 0.05% of reading and a bit of full scale, and it's fully temperature compensating. And we take a brand A. Well, and it's 0.025% of full scale and 0.015% of reading. So if it's used at the temperature of calibration, it's more accurate. But if you use it in the real world and you take it away from the 22 degrees or 20 degrees where it was calibrated, the story changed because that when you add the temperature effects, you will find out that the small 30 series actually becomes the better ones when these temperature effects are implemented. Again, a bit to think about. And then how do you specify the accuracy? Should it be % of reading or should it be % of full scale? And well, have it your way. Both are valid ways to state accuracy. % of full scale is actually define the same accuracy across the entire pressure range. So a 100 psi gauge will, with a 0.1% of full scale, would be accurate to plus or minus 0.1 psi across the entire pressure range. It is some people actually like it this way and some dislike it. % of reading defines the accuracy as a % of the current reading of the actual reading, and it will differ then across the range. So if you take the same gauge here with % of reading, you see that you actually get a better dynamic range. So if you see, well, okay, at half pressure at 50 psi, it's twice as accurate as the percent of full scale. And if you take it at 20%, it's 5 times as accurate as the percent of full scale. So it would actually offer a higher dynamic range for the user, and it will be possible to calibrate at a higher turn down rate. So it might be 100 psi reference gates must be used for, well, it could be used for both the 50 and the 20 psi ones as well, where they say, well, okay, if you have a 20 psi gates, calibrating them on a full scale, it might be, well, okay, it might call out for another gates. And that's the reason why we sometimes state that the percent of reading actually eliminates additional reference gates. A bit of graphs here. Put it into graphs, it might be easier to do it. Modern high-end digital gates will easily offer percent of reading, and obviously the deadweight testers, because that's actually where it all come from. I would say, in a way, the specification of percent of full scale is kind of a legacy from the mechanical gates, where the accuracy and resolution was limited by the mechanics and, well, the pointer and all that kind of stuff. And today, with the modern digital reference cases and calibrators, we can all take advantage of the percent of reading with the sufficient accuracy and resolution across a broader pressure range. So making that to a small graphics down below, say, well, okay, that's it. It gives a very significant difference of percent of full scale or percent of range. And this is the same numbers it actually had on the previous slides. And then we all end up with calibration certificates. The final proof of quality is the calibration and the calibration certificate. More or less, that's what it's all about. Without a calibration results in a certificate, the word calibration does not make any sense, because what it's all about is to compare a pressure somewhere in the world with a pressure known, in a standard pressure known somewhere else in the world, and comparing them. So all calibrations must be traceable to international standard. If you have a look in the right side there, you will have the SI, NMI, the primary reference laboratories, accredited calibration, and so on, and field measurement in the very bottom. So there would be a pyramid of traceability behind it. And the preferred way to do it is accredited calibration, because the accredited calibration is calibration within a certain accepted standards and so on. But it could be ISO, it could be ISC, or it could EN 17025. And these laboratories are approved by national, international organizations, and their scope of calibration is backed up, and it will be looked after and examined and on a regular basis. So the technical competence of these labs will be high. It will be high to actually maintain the accreditation. And then it comes to the final proof, the calibration certificate. All crystal reference gauges and calibrators include an accredited calibration certificate. And we do them in bar, PSI, or something Pascal related, and say, well, okay, why don't you do them all three? But we're not allowed to do that when we go into the accreditation system, because we are not allowed to recalibrate the pressure unit. So that's the reason why the customers would need to order the calibration certificate in one of these units. Getting back in your memory, we had a lot of talk about the temperature compensation and the equations that went into every unit, and what should happen. How do you actually prove that? And we do that the way that we do with we actually calibrate the calibrators, electrical and on pressure, on the over the temperature range. So this, we actually document that the equation that went into that very unit, if you say that, well, it's actually temperature compensated from -20 to +50 degrees, we calibrate it on a accredited certificate in the complete temperature range. So that's the proof of that the equation we calculated and we afterwards uploaded into the unit is correct. And basically, after this, because sometimes people say, well, okay, we can have that type of calibration in our area, or it would be too expensive. Oh, yes, that's correct. But going forward, well, basically, you can calibrate that instrument at any temperature between -20 and 50 degrees. Normally, it would probably be 23 degrees, but there will be no demands for doing these temperature calibration over going forward, because we documented that the equations that were in there was correct, and the physics of the sensor and basically electronics and so on, we corrected that, and so going forward we just made a standard calibration certificate. And this is what it might look like. This is a well, it's a pressure, intelligent pressure module. This is a clip of a accredited 17025 certificate, and it's, you see here on the left column there, you actually say temperature from -20 to +50 degrees. And you have the reference readings. Well, the pressure range was here. It's yes, it's 300 bar. This one, you can see the indicated range, the division, the relative deviation, and that kind of stuff. And the actually, as manufacturer, we put in a allowable tolerance, and we have the expand uncertainty, which is actually our capability of generating the pressure. And that's a bit worth looking for as well, because basically you can calibrate everything with everything, with even that the uncertainty is very high, but the resulting calibration result will obviously relate to what if the source, the expand uncertainty, is poor. And then we actually have a convenience column over the years that actually say is passed or did not pass. This is our proof of our temperature compensation to have and we do it the same way on all our equipment, and it might be the smallest one or the biggest one. And we also do this for the electrical parameters, for the RTD input, for the milliamps, for the voltage inputs, and so on. So this is well, this is unique. We conclude a bit of this one. Understanding these specifications is essential for choosing the right pressure tool to test verification or calibration. Hopefully, I did not make you more confused, but actually, you found out that this was useful and made your job easier for you and more qualified. I would say thank you for attending this little webinar. It was not rocket science, but I think there was still we came across a lot of questions, and I think that was what I had for today. I was looking, I see here with the chat on here. I think. Look here. Yeah, I think Sean has been taking care of the questions. Thank you, Sean.
Yeah, Paul, we had just two pop up just now. So the first, what is display accuracy? So this term has been mentioned on competitors' data sheets, and what are the factors being considered to derive a display accuracy?
Well, basically, if you have a digital gauge, you say, well, that the accuracy would be the display accuracy. Because I think it originates from the past where you might have some analog things going on, and you might have a digital output and so on, and say, well, okay, you had a display accuracy, but if you take something like a reference gauge, the display accuracy must be equal to the accuracy, because that is what the end user will actually see on the gates.
Okay, great, thank you. Another one here is how do they verify an XP2i? I think they may be asking recalibration purposes.
Just standard calibration way behavior. Do 5 points upwards and back and downwards in your ordinary calibration lab with your controller or deadweight testers. That should be at least 4 times better than the XP2i's specification, preferably 5/8 times better. And so it's not. It's exactly the same way with the XP2i or any other crystal measurement device. What is special is that we verified over the complete temperature range at the initial calibration. The going forward, the calibrations after that do not need this very complicated way of doing it.
Great, thank you. And I also put a link to a return form that's on our website if you prefer to have the factory recalibrate your gauges as well.
Yeah.
We have any other questions for Paul? Here's one, Paul, so how does the XP2i measure torque and depth? Can it display those units?
Yeah, well, we have a function in the XP2i that it's a user-defined unit. So if you have a torque, a hydraulic wrench something, it would be specified that so and so many Newton meters would be equal to a number of bars or psi. And to make that a convenient readout, XP2i and other crystal stuff can actually do what it is. It's a custom unit. So you instead of having the torque in psi, you will actually get it into foot per meter or whatever it should be.
Okay. And another one here, Paul, we have a question as to why some of the calibrators like the Envision HPC50 do not have a 5,000 PSI range. So we move from 10,000 to 3,000.
Well, yeah, because that we do percent of reading, so we need a smaller number to have a flat accuracy over the pressure range. Because if we overlap with the Envision with 0.05% of reading, it will actually the 3,000 and the 10,000 will actually reach each other.
Yep, perfect. Another one here, Paul. Should I remove the battery out every time when I do not use the gauge?
Well, it depends on the time. If you want to leave it there for a long time, I would recommend you take out the batteries. Batteries are not well. I really hate when a gauge is damaged because the battery leaked. But obviously, if you're going to use it next week or in a month or so, and leave it in there. But if you know that you're not going to use it for half a year, something like that, take out the batteries. It's a simple operation, and it saves equipment.
Great. Any other questions? We have one popped up here, Paul. Is it possible to pause and then resume a data logging run on the Envision?
No, not really. No, you should actually stop it and do a new one and do one afterwards, and then you can combine them in the spreadsheets.
Okay, so two separate runs and then
Yeah.
combine them
Yeah.
afterwards. Okay. Anything else for Paul here? Yeah, one more popped up. So how do we calibrate?
We actually the temperature chambers actually go to -20 degrees. So we have the environmental temperature in these temperature chambers will be -20 degrees when they are characterized and calibrated at the end. And the temperature of the system is actually met on a crystal sensor, is measured on die on the sensor on the very pressure sensor.
Okay, I don't see anything else in the chat there, Paul. Thank you. Very nice.
You're welcome, all of you.